Okay, this video is the third and probably the final video on an end-loaded cantilevered beam. And I'll put these together in a playlist. And in the previous videos, I saw for the deflection at the end of the beam, of cantilevered beam, due to load F. And I did that two different ways. The first method was to use the naive statement of Castigliano, write the energy, and then take the partial with respect to F to get the deflection. The second method was not to go all the way to energy at all. Instead, write the moment due to F, take the partial derivative of the moment with respect to F, and then plug that straight into a deflection equation where I've already taken the partials. And we saw that in the video number 2 of this set. Now, finally, what I want to do, I mean, in each case, I was getting the deflection at the end of the beam because of the load F. Now what I would like to do is write an equation which is a function of an x kind of variable, which is a function of location. And I'd like to be able to calculate the deflection of the cantilevered beam everywhere. I'd like to be able to draw this curve. Now, to do that, I have to have a load when I use Castigliano that I can place, quote, everywhere. So what I'm going to do is I'm going to place a load anywhere, where anywhere, the definition of anywhere is whatever value I want to give to that variable called xd. And so xd is the distance from the end of the beam to the place where I put this load q. And what I want to do is calculate the deflection at the place where q is located. But by changing the value of xd, I can place q anywhere, which means when I'm done, I'll have an equation for the deflection at the location xd, where q is located, for a value of q equals 0. And when I can put any value of xd in here I want, I can say xd brought q all the way over to this spot and calculate that small deflection. I could say xd was a tiny number and calculate a big deflection. I can say xd is 0 and calculate the FL cubed over 3EI deflection. Excuse me. I can say xd equals L and bring q all the way over back to the end of the beam and calculate that 0 deflection. We'll probably actually play with that a little bit. So let's see how this works. But the key is I'm just going to pretend I know the value of xd, even though it's a variable. And I'm going to place a fictitious or a dummy load q at that location. And notice q is pointing in the same direction as f. And so by taking partials with respect to q, that will set the positive direction for deflection since q points downward. Taking partials with respect to q will say positive deflections occur down. And since q and f are shown in the same direction, that means positive f's will produce downward deflections everywhere. Negative f's would produce upward deflections everywhere. Now, looking carefully at what is stated in the textbook and what is stated in my notes, it says, if we wish, we can use Castigliano's theorem to find the deflection at a point, even though no force or moment acts at that location. And it's the idea of the dummy load. Okay, and so we talked about that in class a significant amount. We'll just place a load there, eventually set it equal to 0. One question will be, when do we set it equal to 0? Okay, and so this idea is going to let us generate an equation for the deflection everywhere. Now, looking at the picture of the beam again, I'm going to have to write moment equations to capture the energy in the beam. And I've actually got to write my moment equation in two different regions. In the region between x equals 0, because this is where the origin of the coordinate system is 0, moving to the right is positive. Between x equals 0 and x equals xd, the only term that contributes a moment is f times x. Now, when I get into this region, out beyond x equal xd, x greater than xd, then I have a moment term, which is still f times x, wherever I happen to be. But then I have another moment which comes from q acting through a smaller distance. That smaller distance being x minus xd. And so my moment in this region has two terms involving f and q. My moment in this region has only one term involving f. Since I make my cut and look left, I haven't encountered q when I'm in this region. So let's see how that works out. In region 1, I create a quantity called M1, and it is just F times X. In region 2, I have a moment called M2, and it's Fx plus Q times X minus D, just as I said. Notice both of these terms are positive. Both forces point in the same direction. They cause the same sign of the moment. Now I need to take my partials of my moments with respect to the loads where I want to calculate the deflection. Well, I want to calculate the deflection at the place where Q is located. So I'm going to take partials with respect to Q. The partial of M1, which is F times X, that partial of Fx with respect to Q is 0. Q doesn't appear in this moment term, so the partial is 0. I call this quantity dm1 dq. And then the partial of this expression with respect to Q is nothing out of the first term, but the partial of Q times X minus D is simply X minus D. Okay, and so now I'm going to apply the modified version of Castigliano's statement, which says going straight to the deflection, which is effectively done as the partial of U with respect to the load. But rather than taking the partial after the integral is done, take the partial inside the integral before you actually integrate. And so the bending deflection term is the integral of 1 over EI, the moment times the partial of the moment with respect to the load. And this is the bending type term. So since I have two different moment terms and moment regions where these are true, I've got to divide my integral up into two different pieces. And so I've got an integral over the region x equals 0 to xd that involves only the moment number 1 term, f times x, being multiplied by its partial, which is 0, which means this entire integral is going to go to 0, which means this term makes no contribution to the deflection. And then I have my other moment term, which is valid over the region xd, x equal xd to L, x between xd and L. And here's the moment, and here's the partial. So I take the moment and I write it right here. I take the partial, x minus xd, and I put it right there. These two integrals together are no longer energy terms, they're now deflection terms. I go straight from deflections when I use the m times the partial of m formulation. So this is the total, this is the deflection at the place where Q is applied, which is the value of xd. Okay, now this term is going to go to 0. I'm not going to pay any attention to this. But this quantity involves the product of two terms, fx plus q times x minus xd, that entire quantity multiplied by x minus xd. So I'm going to let MathCAD do the algebra of multiplying these things out. So the product of these two, when I let MathCAD expand it, is these 1, 2, 3, 4, 5 terms. And so this integral is going to be an integral of 5 terms. Here I simply make note that the first integral, in fact, goes to 0. And now I'm going to take this quantity right here, rewrite this integral using the expanded version of this term. Here's the integral with the expanded version. Okay, and I'm going to let MathCAD do the integration. And what it's going to do is it's going to take this term, fx cubed, fx squared over EI, and it's going to turn it into an fx cubed over 3EI because we are integrating with respect to x. So we're going to have an fx cubed over 3EI term, and that term is going to be evaluated at L, and it's going to be evaluated at xd. The L term will be positive, the xd term will be negative, and we can see that after MathCAD has done the integration, we have an FL cubed over 3EI that came from this term, and later on we're going to have a minus fxd cubed over 3EI. Let's see if I can find that term. I haven't found it yet. Fxd cubed over 6EI. Hang on, let me look back at this a second. Okay, so this becomes fx cubed over 3EI. So we have an FL cubed over 3EI. The only thing that might happen is maybe, since we have 1, 2, 3, 4, 5 terms to integrate, let's see if we have 10 terms here. Maybe some of them combined. 1, 2, 3, 4, 5, 6, 7. Some of the terms must have combined. There must have been some algebra here. So I'm not seeing the term that I'm looking for, but it's okay. MathCAD has gotten the right answer, I promise you. Now I take the answer that MathCAD got, and what does this mean? This is the deflection of the cantilevered beam at the place where Q is applied, and it does depend on the value of Q. But of course, we place Q there as a fictitious load, and our intent is to set that to 0. So let's take this deflection equation, which is simply copied and pasted right here, but substitute Q equals 0 everywhere, which means 1, 2, 3, 4 terms simply disappear, leaving 3 terms behind. And so MathCAD will make the Q terms go away, and then do a little bit of simplification. And so here is the deflection equation of a cantilevered beam with an end load F. Q has been set equal to 0, but XD is still in here. And XD told us where Q was located, but it also tells us where we're going to calculate the deflection. So XD can now wander everywhere between 0 and L and tell us the deflection everywhere in the beam. There is one problem with this equation, in that I was measuring for this equation all X values from the free end of the beam, not the cantilevered end. But if you look at the problem in the back of the textbook, it says let's place the origin of the coordinate system at the wall, and let's let X travel outward toward the free end of the beam. That's a different coordinate system than we've used, and so I get a different answer. This thing says Y is an fx squared over 6EI times X minus 3L. That's fine. That's probably the truth, but it's not what I've got here. Okay, and there's no way actually that I can massage this into becoming this without a total change of coordinate system. Okay, and so I need to go to a different coordinate system. Now let's look at how to do that. Let's go back to the picture. I'm measuring positive X from the free end. X increases as I move to the right. Instead, if I wanted to, I could have created a variable, and maybe I called it X star. And X star locates Q from the wall, not from the free end. And so I could say X star starts at the wall and travels positively toward the end of the beam, and X star increases as I move toward the end of the beam. So now what I want you to do, you can't see it here, but imagine an X star dimension here. Now X star and my XD together add to the length of the beam. So what I'd like to do is redefine my variable XD in terms of X star, where X star is a quantity measured from the wall, not from the free end. So I can say that my XD is L minus this X star. Okay? So I can go to my equation and I could do a substitution. Everywhere I see an XD in my equation, I could substitute L minus X star, and that's going to give me a new equation. And X star tells me where the load is located from the wall, not from the free end. And X star would then tell me where I'm calculating deflection as well. So I'm about to go sort of make the substitution that this distance, my distance is L minus this new term. And instead of calling it X star, I'm just going to call this XD again. Don't let that bother you. So let's see where I do that in MathCAD. So taking my answer right here, copy it, paste it, but I'm going to substitute everywhere I've got an XD in here, I'm going to change it into L minus XD. Now, could I have called it L minus X star, and I'd have had an X star right here? Sure. I just decided to leave it as an XD. Matter of fact, if I wanted to, I could say this becomes L minus X. And so X tells me where I am from the right-hand wall, and it just makes it look maybe even a little bit prettier. Now, I need to talk about a detail on this one, comparing the back of the book to my equation. Note that I've got a minus sign right here, and they don't. Why is that? In the book, okay, they presume that a positive F is acting downward, and a positive F will produce what direction of deflection? Well, notice the minus sign here for Y max is negative. So this equation comes out to be negative. Why? because x is certainly always going to be smaller than, less than or equal to L. Okay, so x is certainly less than 3L. And if that's the case, this quantity is always negative. And if this quantity is always negative, then the deflection is always going to be negative everywhere for a cantilevered beam. And so they say positive force downward causes a negative deflection, and they make the minus sign work out. But what is Castigliano saying to us, and what decisions did I make in setting up the problem that will affect the sign of the answer specifically? First of all, I have F acting downward. I'm making no decision about whether that's positive or negative yet. But I've placed Q downward intentionally. And since Castigliano gives positive deflections if they're in the same direction as Q, and gives negative deflections if they're in the opposite direction of Q, then Q down produces positive deflections. Now, Q and F are in the same direction. Therefore, if Q is down, F must be down. If Q down produces positive deflections out of Castigliano, then F down produces positive deflections. I'm going to have a sign difference between my equation and the back of the book equation, and we will see that in just a second, because when I do the substitution, let's get there, taking my rough Castigliano answer, copy and paste it, do a variable change so that my new x is now measured from the wall, not from the free end. I get the identical equation that they have in the textbook, but I get a minus sign that they don't have, because my positive Q produced, which was down, produced downward deflection. I'm calling down positive. I'm not calling down negative. So first of all, this term is always negative, which will cancel that negative sign. So my deflections for positive F come out positive. Now, in doing the Castigliano, let's review what happened. First of all, I wrote moments over multiple regions, and I took my partials early, and I plugged my partials into the new form, not of the energy equation, but of the deflection equation. So I have moment times the partial of moment with respect to a load. Okay, but here's the question. In this version, I left Q in there a long time. Q is still in there. Okay, Q is still in there. Even after the integration, which I let MathCAD do, Q is still in there. I didn't set Q equal to 0 until the very last possible moment to come up with the deflection equation. Now the question is, how early can I set Q equal to 0? And the answer is, after I've taken my partial derivatives, I can go back to my moment equations and set Q equal to 0, and I can go back to partials and set Q equal to 0. I can't set Q equal to 0 before I take the partial, because I wouldn't get this term. So I take my partial, and now if I wish, I can set Q equals 0 and wipe out this term. And so my first integral would be moment, fx, times derivative, or partial, which is 0. That term will have no effect. Then my second integral is going to be this thing, but Q set equal to 0. So that's going to be an fx multiplied by an x minus xd. I'll set that Q equal to 0 right away. Let's see where that is. So rework, but set Q equal to 0 earlier. Here is my second integral. It's the only one that has value. Q is in there. But in this next step, I set Q equal to 0. It's no longer in there. This term is gone. And so here is this term. I then multiply these terms together, and I get an fx squared minus an fxxd. Okay, and so here is, so this is the thing that I'm really going to integrate. And when I do this, so Q is gone. Q disappeared. And frankly, in reality, I would never have written it this way first. I would have gone straight to this. I'd have set Q equal to 0 up above and written, this is my moment and that is my partial. And so, integrating this thing, with respect to x gives me an fx cubed over 3ei minus fx squared xd over 2ei. Okay, but this integral, sorry, notice that I have no limits on here. This is the indefinite integral, but I've got to evaluate this between the limits of xd and L. So I plug in L for x in both of these terms, and then I subtract plugging in xd for x in both of these terms. And so when I actually do the real integration, I get this thing right here, which is exactly the same as the one, and I've got a little arrow running up above. It's exactly the same as, scroll a little bit, this term right here. So whether I set q equal to 0 as late as possible, or set q equal to 0 as early as possible and follow through with the math, I get the exact same answer. Now, this answer still has my coordinate system x being measured from the free end of the beam, not from the wall. So if I substitute again that xd becomes L minus x, then I'll get the same equation as the book. All right, that ends this example, which shows, first of all, using a dummy load. It's using it to calculate the deflection of the beam everywhere in the beam. And so, which means I've achieved this equation, deflection everywhere at every possible value of x. And I did it with a dummy load, and I set the dummy load equal to 0 both early and late. And we saw that setting it equal to 0 late works, and it simplified some math. Okay, if we look at this earlier solution, there are a lot of terms there that I've had to deal with and plug in and simplify. Okay, so I don't have all of these terms when I instead set this q right here equal to 0 early. All of this math simplifies down. I've only got two terms inside the integral to deal with, and integrating the two terms produces two terms to be evaluated at the limits, which finally produces the exact same answer. Therefore, success.